Next on our list is the question of how do we deal with getting a product that is not favorable under the circumstances we've talked about so far. So when we looked at hydration or oxymercuration, they both got us here. Alcohol on the more substituted carbon and hydrogen on the less. Well, in the words of pretty much every 2-year-old with a choice in life, I want the other one. I want the other one. So our question becomes, how are we going to get here? We need to reverse what would be the normal reactivity. So in the top case, what we've seen already is we either have basically something behaving as a nucleophilic hydroxide, what will end up as the alcohol, in the hydration and in the oxymercuration. This is water, and then a proton's removed afterwards. And we have something behaving as if it were the hydrogen, because this works with what would be that pseudo-resonance structure of our alkene, where we have something that looks like this. Now again, this is not a good resonance structure. I said that when I introduced it in the first video, but it helps us explain some things regiochemically. The better cation is on the more stabilized site. Anions work exactly opposite. So what's good for cations, bad for anions. So we can't change that. The priorities, the preferences electronically for a cation and an anion on a structure are not alterable. So we did use something with the oxymercuration that we're going to have to think about more often, and this is the case where we're going to do it as well. At the beginning of oxymercuration, we used the mercury compound and then eventually knocked it off and replaced it with the H. So we essentially used the mercury as a surrogate for the hydrogen. So if we look at conceptually what we're going to require in the bottom case, we're going to need something to behave like this. That's a weird one. And that's generally a clue that we're going to have to do this by some sort of surrogate method. We've never seen an OH plus before. Doesn't really make sense. And an H minus. Now, the H minus is less of a problem. Okay, weird. Let's have a look. So you're used to this. Let's drag this back a long way to intro chem. Oh my God, electron configuration. I thought I would never have to see that again. Yeah, pretty much, but okay. And we use it as an acid quite often, at which point we're dealing with only a proton. We have no electrons left at that point. Well, if hydrogen had an extra electron, which is to say it would be the H minus ion, well, that would be this, which is the same configuration as helium, a noble gas configuration. If you remember back any of that electron configuration stuff from the past, noble gas configurations are good. So that means that this cannot be that ridiculous. It is certainly less common. It requires some fairly special conditions, but a hydride, the H minus ion here, is really not that obscure. So we're not going to really need a surrogate for that. We've got a lot of things where we can manage that, one of which we even talked about already with sodium borohydride before. The other piece, OH+, that's a freak of nature. So we're going to have a problem with that one. We're going to basically have to have something, I think, as a surrogate there that can get knocked off by an OH or an O later on to give us that OH behaving as if it were an OH+. So let's take a look at how we're going to manage that. The way that we do that for hydration looks like this. We start with a reagent called borane. And it's generally complex to a solvent. We'll talk about that in just a moment. That's what this little dot means. It means not formal bonded, but just complexed with. Informally, it kind of hangs out with. That's about really the best you can say about it. And then we're going to have to deal with getting rid of that. So we're going to have a peroxide and a hydroxide. And that's going to give us, when we're done, the alcohol on the last substituted carbon. So that's going to give us the product we want. How it does it is a little bit odd. First, the solvent itself. The hydride reagent itself. This is borane without any help. Notice it is an octet rule violation. The central boron would only have 6 electrons. The coordinated solvent, THF in this case, this is THF. It is tetrahydrofuran. It's just an ether solvent, so it has a lone pair of electrons here and here. There are others, but the point is this is the one that's cheap and available, so you might see it written this way. It is basically temporarily helping out that octet rule violation, because in boron here is sp2. It has an empty p orbital that's not used because there's no way to get a 4th bond out of 3 hydrogens. So the coordinated solvent temporarily uses it. For the purposes of explaining the reaction, we're not going to draw it with that coordinated solvent in place. It's a little easier to see. The other piece of the puzzle is this. Boron's electronegativity is lower than hydrogen. Not by much. But what that means formally is that we could say that this is basically a negative charge, or a partial negative charge. So it's going to behave like this, as if it were a hydride. So that's when we're going to see H-, that is the hydride ion. So if you ever see that word or hear it as I'm speaking, that means we're looking at something that can at least temporarily behave as an H- group. Now, this is the first case we're talking about so far where the reaction is actually synchronous. The hydrogen and the boron are adding to the alkene simultaneously. So remember, our resonance version of that alkene had this look where the cation was on the more stable center carbon. So that means this H- is going to end up on that more stable center carbon. And even though I didn't draw it here in the product, that is where it ends up. I do end up with an H there. So here's how it works. We're going to have something that looks like this. Our alkene is here. Again, we're not drawing that resonance structure, and we're going to have this happen simultaneously, and it's taking advantage of that empty orbital on the boron. So the alkene is going to basically attack the boron. Simultaneously, the boron is going to let go of this pair of electrons, and that is going to become a bond to the carbon. So I've drawn the arrow through that bond to indicate those bonding electrons are going with the H. So what I get is this. I get the hydrogen and a boron group. Now, there are 2 more H's on the boron here. This could do the reaction 2 more times. Some books draw that, some books don't. It really doesn't matter. For simplicity, I'm not gonna. You could just do this. I've seen some books draw it this way. I believe your book might be one that does, where we just write it as Br2. And the R group, of course, is everything else here attached to the boron. So it just happens 2 more times, like what I've drawn in the first step here. Then, well, something's going to have to take care of this boron and turn it into an OH group. And what I have coming in the second step is hydrogen peroxide and sodium hydroxide. That in itself is a little bit of an odd structure. So it's been a while since you've seen it. Here's hydrogen peroxide. And for obscure reasons, it is slightly acidic. So we can actually use the hydroxide to deprotonate it. That's what this combination of reagents is for. And I should say this is also in water, as are most hydroxide reactions, and all hydrogen peroxide reactions are aqueous. So what we're getting out of that is a hydroperoxide anion. A little different than a hydroxide anion, and the byproduct is water. So what we're going to see is that this plays a role in what we're going to be able to accomplish next. So we have our boron compound. So for the moment, I'm just going to label it quickly. And I'm not going to bother with the other 2 for the moment. We don't need it. Remember, the boron here is still technically an octet rule violation. It still has an empty p orbital that's not part of hybridization. So here is how that works. The hydroperoxide ion is going to attack the boron. So that's going to give us this. We're going to get a boron now that is tetrahedral. Now, we're not really being too careful with how we draw this at the moment. I'm not, that is, I guess. And so we got this now anionic boron. And this is a little bit of an unstable state. Peroxides are a little bit weird to begin with. That oxygen to oxygen single bond is generally not considered to be stable. So what actually is happening here is we're going to take this bonding electron pair that makes up the bond to our carbon structure, and it's going to undergo a rearrangement. So that's going to end up shuffling down to the first oxygen, displacing the second one. So what we're going to get is this. Now we have our boron with the two R groups and an oxygen bridging to our original carbon structure where the boron was. So this is the surrogate part. The boron just basically got disconnected from the carbon, and the oxygen that will eventually become the alcohol got connected to it. Pretty good trick. So this can, of course, happen twice more. So we end up with this. So 3 of these R groups are now here. I'm just going to go ahead and abbreviate the last one. Sorry, those are not R groups there. Those are methyl groups. Those should not be R's. Those should be the methyl groups in the original structure. So I'm going to abbreviate the last one as OR here just to make my life a little simpler. Now, at the moment, this is a boron ester. Now, a carboxylic ester looks like this, where we have the acid and we have the acid and bonded to that instead of the OH is another R group. So boric acid is this. It is BOH3, where I now have 3 hydrogens in each case. So in this case, we're looking at a boric ester. So 3 of the H's that would make boric acid are all here replaced by carbon groups. So if I continue, when the reaction is over, well, actually, not even then. We can hydrolyze them as is, but when the reaction is over, we generally would then say, well, the way we get rid of a basic solution and the way we get rid of organometallic things is afterwards what is called workup. So we're adding stuff to end the reaction, and my handwriting is as good as always here, sorry. Even worse with a tiny E pen. So to neutralize the leftover hydroxide, as well as wash out the metals, we're generally going to say, okay, we're going to add dilute acid to this at the end. Well, partially, that's going to give us a case where we can protonate each of these OR groups one at a time. So we basically only have to deal with one of them, and the others are all identical. So if I look at this in the presence of acid, we're going to basically be taking a hydrogen off of hydronium ion here, and that in the presence of water, still acting as a nucleophile here, is eventually going to take that out. And I'm combining 2 steps here just to make it a little simpler and quicker. But the idea here is that I'm going to end up eventually with boric acid after a couple of neutralizations and my alcohol. So this is the conversion of the boron group to an alcohol. So final product here looks like this, where now I have a hydrogen on the more substituted carbon. I have an alcohol on the less substituted carbon. So this is exactly the opposite of what I saw for oxymercuration. More specifically, and importantly, this is a reaction where I have stereo control. Because the reaction occurs at the same time, it also must occur on the same face. So if I do that same reaction here, what I'm going to get is this. I'm going to get the syn addition of hydrogen and OH. They add at the same time, and therefore the boron is not displaced. The rearrangement doesn't alter the stereochemistry, and we end up with a syn addition of hydroxide, but opposite to the electronic preferences that we would get by simple acid hydration or by oxymercuration. So it gives us a way to reverse those regiochemical preferences, and it gives us a modicum of stereo control. Relative, of course. This is always going to be plus the enantiomer.